Hey everyone, so I thought I'd begin our discussion of the deep ocean by finding the absolute shallowest point I could in the ocean and give us a good running start from there. Actually, the reason I'm here is because I want to start off our discussion with something really important, and that's that muck I'm standing in right now that's gonna take me away if I don't step out of it pretty soon, and that's sediment, all right? And I've thrown sediment, that term, around quite a bit, and I told you guys, hey, just think of that as mud for now, which actually, as we're out here, is pretty true. But sediment's something else, and it's pretty important in the ocean. So simply defined, sediment is particles of organic and inorganic matter that accumulate in a loose, unconsolidated form. Okay, that sounds pretty weird. Like, what does that actually mean? Well, I'll tell you what, let's take a look at it. So if I take something, just a clear plastic tube, which incidentally is a real oceanographic research device, and I stick it down into the sediment, I can pull up and look at it, right? So think about taking a straw and sticking it into a milkshake and just sort of holding the top. This does get pretty messy, so I went ahead and already did that. And I have a sediment core right here. That's what we call this. We call this a sediment core. And this enables us to look at the way the sediment falls. So that accumulating in a loose, unconsolidated form is really important, because what that means basically is it settles, all right? It settles over time. So the youngest sediment is up here at the top, and the oldest sediment is down at the bottom. As you can see, it just sort of stacks. And there's a few ways we define sediment. They can either be by particle size, so the actual grain size of what's in here. You can sort of see in there's some bigger particles, the white ones there. I'm not sure if you guys can see it, but there's bigger ones in there and smaller ones. Another way is where it is. So just the fact that there's sediment here at this river output here in Narragansett Bay is a type of sediment. But for our purposes, because we are in oceanography and we want to talk about open ocean, we're going to focus more on where sediment came from, because that's going to tell us a lot about these planetary processes, these big processes we're discussing. So where they came from, there's four main terms I want you guys to know about this. And the first one is terrigenous, okay? So just like we're here at this river output, the fact that all this sediment, most of this sediment anyhow, came from land, right? River runoff, that's terrigenous. Or it could be from volcanoes or just dust blown out to sea. So you can look at satellite photos across the Atlantic and see these massive dust storms just blowing across the Sahara Desert in Africa and bringing that stuff out to sea. Not only does that accumulate as sediment, but it also actually contains nutrients for some of the phytoplankton that live out there. The next one is hydrogenous. This is kind of rare, but it's just stuff that forms, not spontaneously, but precipitates out in the ocean. What that means is where the sedimentation rate is actually really low, rocks can form. These nodules can just form from the water because of the stuff that's in there. Another one is cosmogenous. Again, this one's quite rare also, but cosmogenous just means it comes from space. So comets and asteroids, they'll hit the ocean, they'll sink to the bottom, and those will become sediment as well. And probably most importantly, at least for a lot of our discussions, is something called biogenous. And biogenous is the remains of organisms, okay? This is things that fall, organisms die and they fall down to the bottom, slowly trickling. Some time ago I showed you a photo like this of the White Cliffs of Dover. Well, that's things like coccolithophores over time dying and just accumulating on the bottom for a really, really long time, and then they get pushed up and form these beautiful cliffs. So that's biogenous. So the reason I took this core is I want to show you something else really special about sediment. Now, the thing is, it can take a really long time for sediment to get to the bottom. So depending on the size of these particles, it can be a few days to over 100 years for something to reach just the average depth of the ocean. Forget about the deepest depths. And what that means is this gives us a record of what's going on above. All right, so like I said, the oldest sediment's down here at the bottom, the youngest at the top. So what we can do is go out in the ocean and take much, much longer sediment cores than this from ships, and we're going to be able to go back in time. So this is like a time capsule. So that's something else as we move into this next module, is we're going to bring time into everything. We haven't really touched on that, and that's incredibly important for the ocean because it enables us to research the history of our planet. So that's what we want to do with sediment. So again, studying this time is something called Paleoceanography. It's a whole subset of oceanography that specifically focuses on our past planet, our past oceans. And what I mean by that is, let's say you have, some sort of nutrient environment in the surface, right? Some sort of that energy exchange, and that's going to manifest itself in the different organisms that live there. Well, when they die and sink to the bottom, they're now trapped. I suppose at least what hasn't been eaten, they're now trapped here. So if I was to take, this section here, and you guys can, maybe you can see this, I'll try and point it out, but there's layers, okay? Different things are happening. There's actually a very distinct layer down here that's mostly brown, then it turns a little black, and then you'll see a band here, maybe some more rocky bits here before you get to the top. So what that means is, where I'm standing right now may have been under different circumstances depending on how far back in time you go. Now, somewhere like here where the sedimentation rate is really fast, this probably isn't back that far in time, but some of the cores we take out in the open ocean can go back millions to tens to hundreds of millions of years. And we can see what was going on all the way back then. What organisms were alive, what fossils can we find, what remnants of the chemical environment are down there. So that's all we're gonna do for now. And like I said, this is a good running start to talk about the deep ocean. So stay tuned. I'm gonna find somewhere a little bit less messy to finish our discussion. See you in a bit. Hey guys, welcome to Module 4, right? The last module in this course. And wow, when you think back how fast this has gone, but think of all the information you've already learned, right? We've talked about so much about the ocean and the earth and life and all of these processes. And for most of that, we have spent our time here, right? In the beautiful sunlit waters, either out in the open ocean or up near the coast or on the coast. And that has been most of our discussion. And that's because, so much life is up here and so many of these processes. But now we're going to move on, right? This next module is all about the deep ocean. And this is important because, well, it's most of the ocean, right? This is the vast majority of the ocean is deep and dark. And we want to go explore it and see what we can find. Now, to do this, I can't hold my breath that long, so I'm going to need something a little bit special. So let's see if I can't. Here we go. I actually have a ride. So I'm going to use this and I'm going to go explore. So you guys come with me. Let's see if door here, I can get in, and I'll see you guys in the deep ocean. Yep, it's dark, and it's definitely deep. It takes a little while, but I think eventually, I think I can feel the bottom. However, I don't see anything. So hopefully somebody can turn on a light. There we go. Well, that's a little bit better, but it's kind of boring, right? This is just a bunch of dirt and rocks. And like we talked about earlier, this is all sediment. And most of the ocean floor is just sediment. That's all it is. But if we start moving around a little bit, all right, we'll start to see things. All right, we'll start to see some amazing creatures. Some of these creatures that either have their own source of light or don't need light, they don't need to see. Some with crazy little lures to lure their prey in that are also lit up. Big teeth, big eyes, all this stuff is pretty amazing. But the important part is the reason we're showing you this is just like all the other environments we talked about, there is a food web down here. There's a trophic pyramid. There's an energy exchange that happens between all of these organisms. And you guys already know this. So where do we get the primary production in the deep ocean? Well, from here, right? These are those hydrothermal vents. These are the amazing output from the ocean's crust of different chemicals that allow life to happen. Right? This is where we can get chemosynthesis. We can use the energy stored in those molecular bonds to create glucose through chemosynthesis. So pretty cool. However, we already know that this is only like maybe 2 to 5% of primary production in the ocean. So this isn't everything. So where else could we get energy from? Well, I'll tell you what, I'm going to show you a short video and then we'll come back and talk about it. So pay attention, and here we go. All right, so this is a whale, or the remnants of a whale on the bottom of the ocean. This was, when this whale fell to the bottom, it became this incredible food source for, you can't see it now, but just an amazing community of organisms. And they use this as their source of energy, source of food, okay? Well, okay, like I said, you can't really see where this came from, so I do have another video. Now, this isn't a whale, and this is in shallow water, but it's definitely more graphic for those of you that are a little squeamish, but also a lot more descriptive. And I'll go ahead and let David Attenborough tell you about this one.
Animals are swarming here in such numbers because of this: a dead seal pup. Such a great quantity of food may only arrive once in 10 years, but a seal's body won't be easy to eat. Nematines have a snout like a harpoon that enables them to puncture the skin of the corpse. It's harder work for the sea stars. They feed by pushing out their stomachs through their mouths. As this sea star presses its stomach against the seal's skin, it secretes digestive juices that dissolve the seal's tissue. But that takes time. These scavengers will feed here throughout the summer until all that remains of the seal will be a skeleton stripped bare.
Yeah, that was definitely a bit disgusting, but it's very important, right? This is what happened to that whale over time. All right, so you can see a figure like this. This is, back to our whale, but there's stages of this decomposition. And we ended up something towards the end of this where there's not much left, and some bones and maybe some of these worms sticking out of those bones. But this process took a long time, and it fed a lot of creatures. However, it's still not much, right? These animals don't fall to the bottom of the ocean very often, and it's a really, really big ocean. So we still don't know how the deep ocean gets its energy source. I have another video for you. So this one's not quite going to be quite as squeamish, but I'll let the video speak for itself, and I'll see you guys back here in a minute. Okay, yeah, if you thought the seal was a bit disgusting, I'm going to go ahead and throw out there that the fact that the vast majority of the life in the deep ocean lives on poop is probably up there. Anyhow, I mean, I say poop, it's not exactly like you guys are thinking of, right? These are biogenic sediment. So this goes back to the sediment that we already discussed. This is dead organisms and fecal matter and other things, but it's very carbon rich. There's a lot of energy there. There's still glucose in there, right? There's all of the things that were made with primary production in the sunlit waters sinking to the bottom and building up over time and creating these sediments. So again, this is biogenic sediment. Well, now you guys kind of know where all this comes from, right? We've talked about primary production in every environment that we're going to discuss in this class, how that relates to energy transfer through the trophic pyramid, and that's it, right? We've sort of taken care of all that. Well, something we haven't really talked about. So yes, all that stuff goes into making glucose, we go through cellular respiration and we get energy. Now again, this is oxygenic cellular respiration. It's very specific, but it's most of the life that you see does this process. And we get energy out of it, we get cellular energy, and we've already talked about this a little bit, and we've talked about a lot of different kinds of energy. Now, some of you have already looked this up. However, we haven't said, what does ATP mean? What is that? There's still something that we don't know. Well, ATP is, all right, I'm gonna have to confess here, I lied to you earlier. You know, earlier I told you there were 4 carbon-containing compounds that were necessary for life, and I made you tell me all about them. Well, there's actually 5. There's one more, all right? And there's something that is called high-energy compounds. And this is what an ATP is. So let's kind of walk through here and figure out what this is. So I want to kind of focus here on the middle part, nucleotide, because we've already talked about this, right? We already know what a nucleotide is. So we've got some phosphate groups, we have a nucleotide, and we get ATP, which is adenosine triphosphate. So let's focus on the nucleotide, okay? You guys have already seen this. We know that there's a phosphate group and a sugar, and it contains one of those nitrogenous bases, right? It goes into DNA and RNA and is part of that code for life. Well, what we can do is, you know, nature is either, if you want to think of it as uncreative or very resourceful, right? We're reusing molecules that already exist inside life. So how does this work? Well, let's look at this figure, okay? So same thing, we have our nitrogenous base, in this case adenine. We have a sugar, a ribose, and we have, let's just say, 1 phosphate. And from here over is our nucleotide that we've already talked about. So this we can call adenosine monophosphate, sure. Well, what we can do is add 2 more phosphates to it, all right? And this right here, the focus will be on these 2 bonds. So really all that means, adenosine triphosphate means a nucleotide with a couple more phosphates on it. Well, these bonds are something called high energy bonds. And the reason they're high energy is because it takes a lot of energy to create those bonds, to stick that phosphate on. But once you do, it stores that energy. So this is why I told you guys a couple lectures ago I wanted to take back one of my earlier analogies, because this is where I want to use the rechargeable battery. So what happens is we take this adenosine monophosphate or diphosphate, either one, and through cellular respiration we get the energy from that glucose and oxygen, and we're able to stick on another phosphate or 2, right? Stick them right on there, and then that molecule now can go to other parts in the cell. Those bonds can be broken and that energy can be used. But unlike glucose, which is converted into something totally different, we still have the adenosine mono or diphosphate. It can now go back and get another phosphate put on, then go back over. So you see this cycle. So this is why I say this is like a rechargeable battery, right? You take your battery, you stick it in the wall socket, it charges it up or adds a couple phosphates. You take that and you put it in something, uses that up, breaks those bonds using the energy, but you still have a battery, right? And you can just keep reusing it. So this is that high energy compound that organisms need for life. And that's adenosine. This is the ATP, adenosine triphosphate. Okay, now I promise that's the last one. There are 5 carbon-containing compounds necessary for life, and we've now talked about all of them. So great. In our last module, we're down in the deep ocean, and we now know all of the molecules necessary for life. I promise I'm not tricking you this time. How all this stuff works. But if you guys know me by now, this isn't the end, right? We still have some unanswered questions. So we know that, the whole periodic table, all these compounds necessary for life, we've carbon and hydrogen and oxygen and nitrogen and phosphorus, right? Well, where did those come from? Right? Each one of those, I told you they're not special. It's just some sort of combination of neutrons and protons and electrons. Well, why did they form like that? And why did they form so neatly on the periodic table? That seems rather convenient. So how did that happen? That's what I want you guys to tell me. So this is your next question, is going to be, where did atoms come from? How did they get that structure, how they exist right now? Not only that, but okay, we find out where atoms come from, and we're talking about the Earth and oceanography and how that applies. Well, where did the ocean come from? Where did the Earth come from? All right. So those are the two questions, multi-part, that I'm going to throw in there for you. I want you guys to tell me where the Earth and the oceans came from. What do you think? How did they get here? And also, where did these atoms come from that make up all the stuff necessary for life, including the environments? So go ahead and think about that. Like I said, this is just one. You guys don't need to look it up. Just sit back and stare at the trees and think about these things. And I want to know your thoughts. I get a kick out of reading these. I really enjoy it. I think you guys are really thinking about this stuff and providing some amazing information. Hopefully this is getting you to look at life a little bit differently. So do that. Go ahead, last module, make sure you are already starting your last homework assignment or getting ready for that final test, working on your paper if you've chosen to do that. As always, please contact me if you guys need anything. Come to office hours for help. Read your readings, watch the videos, and I'll see you next time when we answer these questions. Where did all this stuff come from? See you then.